So I hope you have your answer in your hand. So let's go through this and see if you got most of them right. We're actually going to start with something simple. And it's really the busy state. And in fact, if you think about it, what does it mean to have a busy state? Something is happening already. We kind of explained what can happen. You know, if you're reading into an E state, what do I have to do? I have to tell the current owner to write back their data, and then I can proceed to give you the data. So something is going on now. I can handle it, but all I can do is to send some sort of notification to the current E owner. And we have to wait. That's why I'm in busy state. So, as the name kind of suggests, the handling of this busy state is rather simple. I'm not going to go into all the details. I'm just going to say, well, I'm busy. Come back later. Knack. There's a bit of a special case about a write back. We will see that just a little bit. It's not a knack. You can't knack a write back. Someone is giving you the data. You have to hold it. But the reason that there is a raise is because we'll see that later. Okay, so if we're in one of the busy states, it's actually trivial. Just knack, do nothing. We don't change the state. If it's busy, it's still busy. We're not out of the business. So what about unknown? We already discussed that, right? In the unknown state, let me perhaps erase this to show the text. It's really, the directory will be changing to E state. We have to record who is the owner, because that node, let's say node 3, or processor 1 in node 3 is issuing the request. We need to remember it's processor 3, processor 1, node 3. We of course supply the data. So now the directory state is E. Okay, the owner's state is still pending. It's busy. Okay, it's perhaps I to E. Right, it's in some invalid state now. Okay, it's in some invalid state now, and it's trying to go to, I guess it's trying to go to shared state, right? It says I want to read. When the data comes to you with the node that you're the only one, then I will go from this state, this is a transient state, back into a stable state. Okay, so the next one, think about the next one, right? If I'm already in shared state, I said there were 3 processors or 3 nodes sharing the line, and a fourth one came in. That's actually the easiest. You just give the data, record the presence bit, meaning I have a bit vector, right? I'm already remembering the previous 3 nodes, and now I'm adding the 4th node, and I'm done. What about next? What about the data is in exclusive? I'll give you a hint, right? That's what we're saying here. You're reading a line to exclusive. That's why the next state is a busy state. And specifically it was B1. So what do I have to do? Okay, exclusive. Someone has the data, but yet someone else wants to read it. So the exclusive guy needs to go back to shared state, and the new guy needs to get the data. Okay, so what you need to do is the directory needs to be going back to the busy state. And why doesn't it go back to shared state? Think about that. Have you thought about that? Why doesn't the directory say, well, exclusive, someone wants to read, the next state is shared state, so the next state is shared? Yes, the next stable state is shared. If I change it to shared state right now, what do you think happens? Well, the next cycle, I'm in share state. Maybe someone else will come and read, and I will simply follow what I do over here and supply the data. And that would be wrong. I would be supplying the old data. Okay, so I have to stay in busy state until the current owner writes the data back. So I'm sending the current owner a downgrade request. Downgrade simply means you can keep the data. You don't have to invalidate it, but just downgrade from exclusive to shared. You're no longer special. Now, as an optimization, this system actually sends you a speculative reply, which means this. Here's a piece of data. This might be right, because after all, we don't know if the cache line is having the data in shared state, in exclusive state or modified state. Remember? We don't know. We don't make a distinction. We only have exclusive state at the directory level. We don't know. We don't make a distinction between the two. So the data in cache in memory might actually be correct. So we'll send it to you speculatively. So if indeed we find out that the current owner has not written to it, and that owner may simply send you a request or an acknowledgement to say, yeah, go ahead and use that data. So this might be faster. Next, what if I have an unowned state and someone issues an upgrade request? What does an upgrade request mean anyways? I have the data, I want it to be in exclusive state, right? Is that even possible? If it's not possible, we should perhaps record this as an error, an operating error of the system. So, is it possible? Before you say it's impossible, the directory clearly says nobody has the data. You cannot possibly ask for upgrade. Therefore, this could be a soft error, hard error, whatever. We should record the error. If there are too many errors, maybe the operating system should initiate some sort of checking to make sure the hardware is functioning. Well, but a more likely event is that this is really possible. What happens? It's merely the result of out-of-order message delivery. What does that mean? I mentioned this, I think, a couple of videos ago. It's a possibility, right? I have a cache line, and I want to write to it. Therefore, and it's only in shared state. Therefore, I'm sending a request. I'm sending a request to, okay, let me try to draw this. So this is the directory, and this is the node. The node in question, it's a processor. Okay, this is directory or home. I have the line, it's right here, it's in shared state, and I want to write to it. So I send a message. Let's say this is a slow message. This is upgrade. Upgrade. Meanwhile, something else happened at the node that I eliminated this line. When I eliminated the line, what happens? This is sometimes called a drop. I'm dropping this line. The line is no longer in my cache. There are two things you can do. You can tell the directory, or you can ignore it and drop silently. Okay? Because dropping silently is not wrong. The directory thinks you have the data. All that happens is, all it does is next time if there is an invalidation operation, the directory has to unnecessarily send you a notice. So dropping can be silent. But let's say it's not silent. And that's a good idea. I tell the directory, so the directory next time can move faster. So I send the directory a drop message, right? And this gets out of order. This happens first, 1, 2, I send drop, but 3 it arrives first, so the directory's corresponding line would change from shared state to unowned, right? And then 4 the upgrade request arrives, there you go. That's what's shown here. The upgrade request got reordered with the drop notification. So it's possible. And before you want to say, let's restart the machine, there may be error or whatever, error-oriented operation, this is entirely possible. Okay, so that's kind of one example. All you have to do is to enact it to say, sorry, this update request is wrong, and the requester may want to send you another update request if indeed this was an error, and you go from there. But from an error-free point of view, this can happen. It's entirely possible. Now, what happens when the directory is in shared state? The next block, it's in shared state, and someone wants to upgrade. Well, this is easy. In shared state, after all, if someone wants to upgrade, we simply invalidate every line, right? And then one of them invalidate everybody else except the requester who wants to upgrade. So since there is invalidation involved, don't we have to use a busy state? That makes sense, right? Cache line is currently going to be in busy state. We have to wait for all the invalidation requests to come back before we can officially change the state to exclusive. Yeah, make sense? Actually, this is a slight optimization. We don't have to do that. Why? The only person or the only node that cares about all the invalidation requests are being carried out is the node issuing the request, not the directory. The directory didn't have to know, didn't necessarily have to know. I mean, it can help. It's one way of solving the problem, but it can simply say, okay, eventually that guy is going to be the new owner, because there is not a whole lot of difference. I can go through a busy state and eventually change into pointing to you as the exclusive ownership, or I can change it right now. All that matters is the next request from anybody else, I probably have to send it to you. So I can change it to E now and record who has it. Of course, I need to send the validation to every other sharer. And I can reply with the acknowledgement to you to say, now you have the state. Okay, you can go ahead and write, but if you want to make sure the write is finished, if you want to know when the write has finished, you have to wait for these acknowledgement messages from node 1, 3, 5 to arrive to you. So that's what's happening. Okay? And if it's in in shared mode, you're the first one to come in, you get the E state. All right. What if the directory is already in E state, someone wants to upgrade? Again, what does upgrade mean? Upgrade means I have the shared data and I want exclusive ownership. But the directory says you're in exclusive state. So is it possible? Is it one of those errors again? Is it possible? Well, you probably just saw what we discussed right here, right? The directory changed to the E state fairly soon. So imagine two nodes, node 1, 2, both have the shared state, both want to upgrade, both send the upgrade request to the directory. One of them has to get there first. And then how does the directory handle it? It handles this by changing to E immediately. So what happens the next cycle? The next cycle you handle the other upgrade request. So you're already in exclusive state and you're handling an upgrade request. Okay, maybe this is getting too crowded, right? So it's entirely possible. And you're just merely lost the race. 2 upgrade requests, lost the race. So knock him to say, you know what, you should have received by now my invalidation request. If not, wait. But in any case, you didn't get the chance. It has to be nagged. Okay, so that's exclusive state when you issue an upgrade. Read EX. Okay, so this is somewhat similar to the previous to upgrade, but I don't have the data. So now there isn't any question about it. So the directory is in unknown state. So we're here, directory is an unknown state. Someone wants to read. Okay, that's fine. This is perfectly normal, right? So we give you the data, we record, you're the only one anyways, and you also want exclusive state anyway, so this is actually easy. Change to E, record the pointer to point to the owner, give you the data. That's about all we need to do from the directory's point of view. So the next thing, okay, you're in shared state. A new guy comes in, wants the data as well as exclusive state. So this is actually very similar to the state over here. Okay, we don't need any busy state. We don't need to wait or anything like that. We give you the data, but everything else is about the same. Okay, so that's the only difference. We need to shoot down everybody else. We send invalidations, change the state to E. We reply with data rather than some sort of acknowledgement and indication of how many invalidations you need to receive. Okay, this time we have to supply data. Oops. Weather forecast. The next one. It's in exclusive state. All right. Someone else wants to read the data and to have the data in exclusive state. What do we do? Well, this time the handling is similar to the case early on when you want to read the data. We resort to busy state. Okay, we change to a second busy state. And this time we send a validation request to the current owner. Okay, because the new owner wants exclusive state. And we send you the speculative reply. So that's another busy state that we were using. Now finally, what about writebacks? What if it's in unknown state? Directory is in unknown state. But then somehow there's a writeback. Again, is this possible? Well, before you say impossible, think about the case early on, right? Directory thought nobody has it, but it's getting an upgrade request from someone. Is this some sort of out of order message again? Well, if you think about it, this time it's impossible, right? Because oh, okay, this was erased. So because back then it was, there's a node and there's the directory. The directory, the node first sent an upgrade request and then sent a drop notification. Okay, that's how it became, that's how the directory, this was done second, but arrived earlier than this message, right? But this drop request, it's easy. You can drop it, and then the directory becomes unknown in the unknown state. But if it's a dirty data or exclusive data, okay, if it's dirty data, you cannot drop it. You cannot drop the line. You have to write back. Okay, so this is actually impossible. Oops, this is impossible. Okay, because your write back indicates that it's in modified state, not just exclusive. It's a modified state. That's why you want to write back. Therefore, you cannot possibly have dropped it earlier, and the thing gets routed out of order with. This is an error. So you might want to write this in an error log or start to initiate error testing. Next, suppose the data is in shared state. Okay, it's in shared state. And then we want to do write back. Is it possible? Again, it's impossible. This time, just like the previous case, it's impossible. No matter what sort of out of order cases, you won't have this case. So don't have to worry about that. What if it's in exclusive state and it's doing a write back? Okay, it's already in exclusive state and you're writing back. This is actually simple. Okay, it's great. Now it becomes unknown because you wrote it back. We acknowledge. So finally, let's think about this case. Suppose we're in a B state and then you're writing back. This is simply a race. What that means is we're in a busy state, meaning we're hoping you will write back. You will respond to the request to write back. Okay? And this is your write back request, independently issued. So you're trying to write back. Meanwhile, we send you a letter to say, please write back that line. And they just cross path. Okay? So it's a race. So that's very easy. In fact, it's just like in the busy state. And we send you a write back request and you responded to it. Okay, so nothing is special there. And from the busy state, depending on which case of the busy state it is, and then we go back to the corresponding stable state. So to summarize, the directory side has corner cases, right? We give you an example. There's an upgrade request, but the result is in unknown state. How did that happen? Right? That's corner case consideration. At the requester side, this is really saying how the just an example, right? I have the directory side handling the case, and then we have the requester side being a different entity logically, and we have to handle the state. It has all kinds of different out of order consideration as well. But really, this is logical distinction. The directory side, requester side, it's all the hub. Okay? Because our machine is not the dance hall organization. Remember, dance hall organization means I have an interconnect and I have a memory here. And then it has a controller, maybe directory controller. Okay, memory. Then here you have processor, and they're connected. This is called a dance hall organization. Logically, this is what we think about, right? You have requester, you have the responder, but physically, as we can see in the example of R10K, this and this, maybe I use a different color, this is in one node. Okay, everybody has a little bit of a shared directory, and okay, this is painful. That's all you have. You have this type of machine. It has a little bit of memory and the directory, and it has processor. It's all in one node. And you have many of these nodes connected on the interconnect, and that's your machine. Again, try to leverage commodity component as much as possible and not having to design two types of nodes. Okay, so at the directory side, we explain all this detail. Or the requester side, you also have all kinds of out of order consideration. I strongly suggest you to sit down and think about all these cases, except swapping out these directory side states with cache side state. Okay, but we're not gonna go through all of that. So this shows you some complexity, right? Oh, we have so many different states beyond just stable state. We have these states, right? Again, this is really just an example. This is not trying to say that's what the state of the art is. This is one state transition diagram that I obtained from a student thesis, and his name is Lepak. I believe he graduated from University of Wisconsin. This is what's shown in his plot, and I cannot fit the whole thing in the picture. As you can see, these are all, if I can zoom in, these are all state. Here's invalid, maybe you can see that. Here is who knows what, right? There are all these different state. It's a MOSI protocol. Okay, we know MESI, we know MOSI, we know it's just the stable state 6. There are 401 different transitions, as you can see. These are all transitions from one state to another. When this happens, you follow this path to transit, and so on and so forth. So real system is really potentially more complex. So this brought in a different school of thought. It's actually fairly interesting. The two sort of chief architect, lead architect of these two systems, the GS320 from DEC Alpha, by that time it was bought by Compaq, which obviously later on got merged with HP, and then HP subsequently split again. But this was one end of the design spectrum. The Origin 2000 was sort of on the other side. The two lead architects came from the same group, John Hennessy's group in Stanford, doing the prototype called Dash. They brought a little bit of different philosophy to it, and the idea is we're going to design a machine that serves just the low end. We don't want the scalability. Okay, so the machine is going to sell at this size. We're going to have a global switch rather than very complex, flexible interconnect. Each node is going to have something called a QBB, a quad processor building block. Has 4 processors, and that's this blown up to that. You'll see there are 4 processors with their L2 caches. This is back when the integration density wasn't high enough, so your on-chip cache is L1, at least for HP that was the case. No, sorry, for DEC it was the case. The L1 was on chip, the L2 was off the chip. There's a local switch, there's some memory unit there, and boom, it's connected to the global port and to the global switch. And that's it. It's an 8x8. So you can have up to 32 processors. You can't buy a 1024 machine. The idea is we design for one machine, we forego scalability, and system becomes much cheaper, much more controlled. Okay, and the way they do this is the following. They have, even though it's one global switch, it's separated into different channels. Okay, and the channels will, oh, by the way, the coherence is still a directory-based protocol. We know who to contact. The protocol is 8-bit presence vector. Okay, that's easy because I have 8 nodes, 8 bits, done. Okay, so it has the directory. Every node has the processor, a little bit of memory, the directory, which is shown here, the directory, dir, and some pending state buffer. There's all these transactions that's in transition, transient state. So those are called transaction in transit table. You have this table. Normally that's part of your directory controller anyways. This is just being more explicit in showing it here. And then you have a duplicated presence vector inside the processor. So we know who has what. Within one node, we have duplicated central tags. So we have some tags here to see who has a copy inside. So invalidation comes in, we check that tag, and we decide which processor to forward an invalidation request to. The duplicated tag is also part of your node, and it's shown there. Okay, so that's your QBB, your quad processor building block, and you have eight of those, 8 of those, 1 to 8, and then you connect them together for a 32 processor system. It's not the scalability that is the key thing. Another key thing is the switch tries to do, since it's so small, we can control it. Okay, we can make it in order. Remember all the problem that we had because messages can be delivered out of order? What if we give you something in order? All right. And so they realize not all requests need to be falling into some global ordering. So instead of doing that, they divided the physical channel into 3 virtual lanes or channels. And the important one, the ones that you really need to figure everything together into a global order, is the reply from the home node, from the directory. And that's the channel Q1. Every single message sent from every directory is globally ordered. So you don't have to worry about something getting out of order. Other channels are point-to-point ordered. Okay? Q0 is point-to-point order. What's Q0? Q0 is where I send my request. Okay? Well, this is sort of gone, but I was drawing this thing over here. This is the directory, and this is one node. The directory sent one request that got in later than a subsequent request that it sent because it went through a different channel. This is not going to happen. Okay? So a request will go through Q0 channel, and it's always ordered. So if you send it earlier, it will arrive earlier. So in the case that I sent a upgrade request, it will arrive there first. I will not have the case where the upgrade request arrive at the node where I'm already in unknown state. It's not going to happen. Therefore, I get rid of busy states. I get rid of these nags. I don't have to deal with them. That's their idea. Now again, this time I want you to take out a different sheet and think about it. Knowing what we said, again, the directory can be in several states. In this case, because we don't have nag state, there's only 3 states: the exclusive, shared, and unknown. And that's your 4 requests that we always have: read, upgrade, readx, and write back over the P line. Now you fill this in and see how that makes things perhaps simpler.